In part one, we looked at what is a bridge and what is a bridge engineer, and what does a bridge engineer do and what sort of skills does he need. And in part two, we looked a little bit at the bridge in context, the social, cultural, environmental, physical issues that create the constraints in which the bridge design has to be done. This time, we're going to look at the structural aspects. How does the structural engineer go about creating a structure which is going to satisfy all the various constraints? For me, I always start with the long section through the bridge centerline. I find that the most valuable thing to do is actually to draw a plan with the sort of, if it's a river, let's say, and the key features on it. Maybe there's a footpath along one side and there's a railway on the other side, perhaps. And this is the position that the analysis of the site, the context, has shown us is where the bridge needs to be and the sort of bridge it is. There's a navigation channel down the middle, and very often it's all about identifying what are the constraints that are really going to be the controlling factors on the bridge alignment and so on. So let's say it's the navigation channel. Okay, that's going to have a clearance. Let's say they told us that how high the ships need to be or the boats need to be. We've got a railway line, that's got its own kind of clearance. There's a footpath, that's got its own kind of clearance. We know that there's probably a limiting gradient as well, so we can't be too steep. So there perhaps is our longitudinal profile. We've got the buildings and so on in the background. So if you like, that is the constraint diagram. I can now begin to think about where do I put some supports? How do I support this line, this profile, this surface that is the bridge? The other important drawing that we have is the drawing of the cross-section, or more specifically, the functional cross-section. And this is where we decide what happens on the bridge deck itself. And so if this is a road bridge, for example, it may be a bridge with a footway on either side, and you could imagine that you've got cars and vehicles in 3 or 4 lanes, whatever it is. Maybe there's a cycleway. And so that's your functional cross-section, which defines the width of the bridge. And you can begin to put a bit of scale on this. What does a person look like on that scale? Before I even actually start thinking then, okay, how am I going to support that surface? And you need to be thinking about both of those at the same time. Imagine now that here's my line, and this is a line which, if it's an infinitesimally small, thin line, it's not going to span very far. It needs a depth to be able to span the distance. How far is that? So you're going to need to look at both the cross-section and the long section at the same time. Maybe we think that actually the site demands a large bridge, so maybe we're going to span from end to end. I don't know. Why don't we do something like an arch? Maybe that's not entirely ideal, but it's something. But we've then got to support the bridge deck with some hangers, and the deck can be quite thin because we can support it at close centres. But another option, of course, might be to say, okay, well, actually what we're going to do is we're going to just do the minimum span that we can get away with. There's that line again. Now we can support it here and here, assuming we can build foundations in the water. And maybe we put another support at the edge of the river, and maybe we've got another one back here somewhere. And all of a sudden, we've got what looks like a kind of fairly conventional continuous bridge. Yep, very simple. And that depth is a different sort of depth to the depth we had in the arch solution. By and large, I tend to look at the depth being something like 1/20th or 1/30th of the span, something in that sort of range, depending on whether we have continuity or not. A continuous beam, you might have 1/30th of the span. If it's a simply supported beam, it might be rather more. It's a 1/20th. But of course, thinking about the cross-section now, going back to my cross-section diagram, I now need to think about where does that depth materialise. So here's my cross-section again, very crudely drawn. I always like to show a little thin edge. Everybody does. It looks nice and slender to have a thin edge. But let's say this bridge is going to be supported by some sort of structure along the edges. Maybe this is sort of beams. These are the beams which I was drawing earlier on. I need to think about how deep does this need to be in order to span transversely, because this surface needs to span in 2 directions, transversely and longitudinally. So there we are. There's a solution, a rather crude one. We probably need to have more than 2 girders if we did that. We might need to have a different kind of solution altogether. You could, for example, imagine something which would look more like this. Okay, maybe it's a box structure. You know, I'm only drawing very crudely, but you could imagine the number of different options that would do the same thing. Now this structure here is a deeper section. So each of these solutions responds to the need to span longitudinally and transversely, and both of them have structure underneath the surface. So if you were on the bridge as a user of the bridge, you wouldn't have anything over your head, and sometimes that can be a bit disappointing. So another way of doing it, I mean, perhaps going back to the arch solution, would be to have structure over your head. And so what that would look like would be still got the same functional cross-section, we're still having to carry the same things, but now you've got to think about where the structure is going to go overhead. And one option, for example, would be to put the structure on the centre line. If you do that, of course, you're going to need to have torsional stiffness so that the thing doesn't twist under eccentric load, so then we're going to have to make this into a box structure. So that's fine. That is one kind of structure. Another way of doing it, of course, would be to have structure down each side. And that is why I say you need to be thinking of both the cross-section and the long section at the same time. So you could imagine a cable-stayed solution, for example, with stays either side of the roadway. Obviously you have crash barriers and things, as indeed we would have had safety barriers either side of the stays in the other solution as well. But if those could be stays, then our girder is here. I don't know what sort of shape this might be, but you could imagine maybe you've got some sort of girder at each edge, and now this doesn't need to span so far. I don't know, we could do something unusual with it, and so this is our longitudinal element, and so on. And in the elevation, if you go back to that, that then says, okay, well now maybe we're doing a cable-stayed bridge in my elevation. And so where do we do it? Should we put our masts here? We put our masts there, and we're going to do cable stays and so on, whatever we do. And there's a cable-stayed bridge solution. So the answer is to look at both the longitudinal and the transverse at the same time, and you could come up with a whole range of different solutions where this drawing, the plan and long section drawing, is very important to be able to understand where the constraints are, where you can put the foundations and where you can't, what you're trying to clear and what you aren't. So the other thing we could do, imagine this is a footbridge, which obviously has a very different kind of scale, and scale, as we know, is an important factor. And so now you could imagine, let's say we put a person on here, and there's the handrail, and there's the other handrail, so we've got something which may be, I don't know, 4 or 5 metres wide. And like before, this surface has to be able to span transversely between whatever structure is holding the thing up, and longitudinally. We can use the same longitudinal profile that we had before, but of course we've changed scale now, so it may be things are different in plan, but let's just draw this again for the sake of argument. So let's say we've got our same profile. Remember, pedestrians are very gentle gradients. And now, if we're going on the same sort of site, I don't know, perhaps we might have been, because it's a pedestrian bridge, we can do different sort of things, and maybe the site actually lends itself to a rather different approach and possibly gives us a curved alignment. Why not? Pedestrians like going around curves. I always like going into a bridge where you can't quite see out the other end when you start. Not quite sure where you're going to end up. So now you might say, okay, well, what sort of structural system will satisfy these constraints? We've still got the navigation channel, we've still got the railway line, we've still got a footpath for the sake of argument. And now maybe, I don't know, maybe we can say we'll go for a big arch, shall we? Should we go for a big arch? Oops, not very well drawn. Also because it's a curve, we maybe, let's say, do it as an eccentric arch, an arch that comes off one side. Now, this is the sort of thing which we do when it's economic and sensible to do it, and also where the site demands that kind of approach. What that does, of course, is that immediately when we come to our cross-section, is we then have, now we have supports along on one side. So our hangers coming from the arch, which is up here somewhere, are on one side of the bridge. That means that this thing has to have some torsional stiffness. You've got to restrain it from twisting at the ends, and you need to give it some sort of a box structure. So maybe it's a box girder here, maybe it's a steel box girder. So that's all a hollow box, and we've got some lightweight cantilevers on the outside. But the purpose of saying that is that this again is another illustration of how the cross-section, the long section and the plan all have to be taken into account together. Where is the longitudinal support? In this case it's the arch, and how does the cross-section have to deal with that? Incidentally, another rule of thumb, if you're spanning like a cantilever, as this one is, then I tend to think in terms of something like 1/6 or 1/7 of the span is the sort of depth that you're going to need at the root of your cantilever. But that is another way of solving the problem. We're dealing with the functional cross-section, we're looking at the plan elevation, and like I said before, you're looking at all three at the same time: cross-section, long section, and plan. So we've seen that there are constraints on the site which will determine where you can put foundations, and that will determine what the span lengths are. And there are basically 5 different types of structural system then that will support the bridge deck in between. The longer span solutions tend to be suspension bridges, where you have towers and a cable which suspends between them, and then the bridge deck is hung from that cable. You have cable stayed systems, where it's also a suspension type of system. The bridge deck is suspended directly by cable stays to the towers. Then you have arches, of course. There are different kinds of arches. And the fourth type, I suppose, is generally called trusses, different kinds of trusses you could have. And then finally, is a simple beam. And of course, simple beams tend to be at the short end of the span spectrum, and the suspension bridges tend to be at the long end. Of course, the decision on which of the 5 types to use is going to depend upon a number of factors. And for example, the suspension bridge, although easily the longest span solution, may not be appropriate because the ground conditions may not support the horizontal forces that are exerted from the cables on the anchorages at each end. So a cable stayed bridge might be the appropriate solution. Equally, construction program is usually an issue, and if you've got to build quickly, then a cable stayed solution is faster to build than a suspension solution. Materials is another factor. The long spans will want to be lightweight, and therefore steel is likely to be the solution. You may find that there isn't a big steel industry where you're building, in which case there may be a different factor that would be a factor to take into account. Concrete may be more suitable for the shorter spans. So by and large, there are lots of different factors which the engineer is going to need to take into account. We've talked about vertical loads and how the bridge needs to carry the weight of pedestrians, vehicles, itself. But of course there's also horizontal forces, wind and earthquake if you're in an earthquake zone, sometimes impact from vessels and other horizontal forces, the braking loads from lorries for example. All of those need to be taken through the structural system down to the foundations, and the engineer has to consider those at the same time as all of the rest. The other thing to note is the design process is not a linear one. You don't start at the beginning and go to the end. It's an iterative process. You're constantly going back to something you've already done and thinking how to make it better. You can get quite quickly to a design solution, but then, and that's the kind of 10% of the exercise, and then the 90% is about refinement and perfection. And this is where the overseeing mind, the one person who's overall understanding where we're trying to go with the bridge, how we're going to get that little magic in the elegance, how are we going to get that detail. In this short series of videos, it's not been possible to cover every aspect of bridge design, of course not. But I hope you've been able to see an insight of how I approach the challenge of designing a bridge to deal with the environmental and social and cultural issues, as well as the physical and mechanical ones, so as to end up with a bridge which is not only functional and strong and safe, of course, but is also delightful.